Alright, so we're going to look at concavity and trig functions specifically. Okay, and what we're trying to do is just get familiar with the idea of concavity and also see a couple little tricks that'll help us understand what's going on inside the trig function and help us hopefully link concavity. So trying to combine a couple of pieces of knowledge here, a bit of recall and a bit of new learning. So we're going to look at a really simple, really simple function of y equals sine x. And we're going to look at how does the double derivative, or how does the concavity change throughout that function. I'm going to derive that first and I get cos x. Okay, so the derivative of sine x is cos x. Derivative of cos x is negative sine x. Now I could have picked any function. I could have picked sine x, cos x, negative sine x, negative cos x. It doesn't matter. Whatever function I put there, my final value would have the negative of that. Now that will change if I've got values out the front and inside and all that sort of thing. But for a simple baseline function, that will be what it looks like. Realistically, we don't need to know anything more about that. I'm going to reference it when I talk about our graph because I've drawn all three. But we really just wanted the concavity, we just want that double derivative. Okay. So here I've drawn earlier our functions. I've done the cos function in blue with the dots. I've done the sine function in the black pen, and the red pen has my negative sine function. So my black is my function, my blue is my derivative, and my red is my double derivative. So let's first look at the black function. Obviously, it goes up, it forms a maximum. That occurs when our derivative function equals 0, which we can see. Okay, it forms a maximum at pi on 2. Back down to 0, minimum at negative 3 pi on 2, back to 0. So we know that our trig functions tend to follow that repeating pattern over and over and over again. As I haven't got a value in front of my x, I can see that I'm going to have one period is going to occur over a period of 2 pi radians. Okay. Now, beyond looking at the fact that our cos function equals 0 at our max and min point, we don't need it anymore. So I'm actually going to rub that cos function out because I don't want that distracting us from what the real go is with this. So the real focus is about a derivative function and a double derivative function. Now what I'm going to do is just put little dashes through our red function, which is our double derivative, just so we can see more clearly and be reminded that that is our double derivative function. Okay. Now again, you'll remind yourself with concavity, it's all about the shape. So if it's got an N shape or a U shape, we talk about upward and downward concavity. The way we find that out is with our double derivative function. And it's not about the size, it's about whether it's negative, whether it's positive. Okay, and that's what it's all about. So we're just looking at our red function being negative or positive here. As we can see, our sine function, our black line function, that is in that N shape. Okay, that's what we call upward concavity. That occurs when we have a negative double derivative. So anytime our double derivative is negative, we have upward concavity. As you can see with this function here, throughout that entire period between 0 and pi, our double derivative function is negative. Okay, so we have upward concavity between 0 and pi because our double derivative function is negative the entire time. Now, at pi, both functions equal 0. That happens to be a point of inflection because our concavity is changing. We're no longer in an upward concavity. We're now in a downward concavity. That occurs when a double derivative equals 0 and is going from a negative to a positive value, or vice versa. So as you can see here, our concavity or a double derivative function is going from negative to positive. So at this point pi, we have a point of inflection. From that point on, there is a downward concavity. So you can see it's going to form that U shape. There is a downward concavity for the remainder of that time. That aligns with what we see in the double derivative function. That function is positive between pi and 2 pi. The entire time that has got a positive value, which makes that upward concavity. At 2 pi again, we're going to have another point of inflection where they're going to swap over. So our concavity is going to go from positive to negative. We're going to get a point of inflection which is going to turn our downward concavity into upward concavity. So the main takeaways I want us to get out of this, okay, is that obviously concavity and trig functions, just about reminding us of what those things are. I wanted to highlight the double derivatives work. It works for whatever function we're dealing with. That tells us about concavity. Reminder that a negative concavity a negative derivative function means that we have an upward concavity, and a positive double derivative means that we have a negative concavity, a downward concavity. A little trick for our trig functions is that by nature, whatever our function fx is, we're going to get the negative of our original function fx as our double derivative. Hope that helps. It's good conceptually, good reminder. Hope that helps you get your head around the idea of trig functions and concavity.